All right, today we're diving into the science behind something most of us never even think about: the invisible armor that protects pretty much everything we rely on. We're talking about high performance coatings. So, what exactly is this armor, and what does it do? I mean, have you ever really thought about that? Why doesn't the paint on a jet engine just give up and peel off when it's freezing cold up at 30,000 feet? Or, why doesn't the special coating on a surgical implant flake off? The answer, it turns out, is way more interesting than just a good layer of paint.
Yeah, these things are not just for making something look nice and shiny. We're talking about incredibly complex, engineered systems. They're designed to fight off friction, corrosion, and wild temperature swings. They're a critical piece of modern tech, from the planes in the sky to the medical devices that save lives.
So that's the million-dollar question, right? How can we be sure this armor is actually going to work when things get really tough? You can't just cross your fingers and hope for the best. You've got to prove it. And to do that, scientists put these coatings through some absolutely brutal tests.
The first gauntlet these coatings have to run is all about surviving sudden, violent change. It's basically a trial by pure shock. So what do we mean by thermal shock? Okay, picture this. You take a glass baking dish right out of a super hot oven and plunge it into a sink full of ice water. That horrifying crack you hear? That's the material literally failing under thermal shock. And coatings on a jet engine? They go through that on every single flight, from hot tarmac temperatures to 50 degrees below zero in just a few minutes, and then right back to scorching heat. And that's exactly what these tests are for. It's all about guaranteeing that when this stuff is out in the real world, facing crazy, unpredictable weather, its protective armor is going to hold up no matter what. Next up, we move from sudden change to just pure, sustained, intense heat. And this isn't just about whether it can survive, it's about finding its absolute final breaking point. See, researchers have to know exactly how much a coating can take, so they don't just, warm it up a little. They blast it in controlled furnace-like conditions to pinpoint exactly where and how it finally fails. Let's talk numbers. First up, 400 degrees Celsius. That's around 750 degrees Fahrenheit. At this crazy temperature, scientists run erosion tests, watching how the surface physically breaks down and wears away under all that heat. But oh, they don't stop there. Not even close. The temperature gets cranked all the way up to 850 degrees Celsius. That's over 1,500 degrees Fahrenheit. There's a process called a dry Coronodi test, where they basically bake the coatings at this insane temperature for up to 6 hours, just to see if they have what it takes to last. And, it's not just about the raw temperature. More advanced tests, like cone calorimetry, look at performance under intense heat flux. They start asking much smarter questions, like how long does it take before this thing actually catches fire? How good is it at insulating whatever is underneath? And maybe most importantly, when it does burn, does it form a nice, stable, protective layer of char, or does it just crumble into ash?
Okay, so we've looked at these big external threats, right? Shock, heat. But what if the biggest danger wasn't coming from the outside at all? Turns out, some of the worst failures happen because of pressure building up from the inside. Now, this is where it gets really interesting. You can have the toughest coating in the world, but it can still fail catastrophically because of forces you can't even see, a kind of hidden tension that's been locked inside the material since the day it was made. This hidden enemy has a name: residual stress. The best way to think about it is like a constant, invisible tug of war that's happening deep inside the coating. It gets created when the material is being made, or as it cools down, and it can get worse over time from simple wear and tear. This internal stress makes the coating weak from the inside and vulnerable to cracking. And here, you can see exactly how a good coating fights back. In friction tests, a surface with no coating gets way, way hotter where it makes contact. But look at the coated surface. It actually lowers the temperature. And that is huge because less heat means less stress building up inside the material. The coating isn't just playing defense from the outside, it's actively managing the pressure from within. So we've got thermal shock, we've got extreme heat, and we've got this sneaky, hidden residual stress. They all play a part in whether a coating makes it or breaks. But is one of them more important than the others? This is really the question all this research has been leading to. If you could only fix one thing to make coatings stronger and more reliable, what would that one thing be? And here it is, the answer, plain as day. When scientists broke it all down and analyzed every single factor that adds to that dangerous internal stress, one thing was responsible for more than half of the entire problem: temperature.
Let that sink in. The single most important takeaway is this. Temperature effects, whether they happen during manufacturing or out in the field, account for over 51% of the internal stress that can literally tear a coating apart from the inside. It is without a doubt the number one enemy.
And that brings us to this statement, which really sums up the whole challenge for engineers. The goal isn't just to make a coating that feels hard or can take a lot of heat. The real goal is to design a whole system that is stable on the inside, free from those destructive hidden forces that are caused primarily by heat.
So that leaves us with one final exciting question. Now that we've identified temperature as the main villain in this story, the race is on. The hunt is on for the new materials and new processes that can finally conquer it and lead us to the next generation of armor that's not only invisible, but truly invincible.